So we're now starting to think about symmetry and why it's so important in quantum mechanics. And I'm going to run through a number of examples of different things. We're working our way toward hybrid orbitals. But let's start again with the simplest of all interactions of two separate s orbitals interacting to form a sigma and a sigma star, where of course we wind up putting a stable configuration of two electrons anti-aligned with opposite spins in the sigma orbital. So we have a sigma Gerada 1s and a sigma Ungerada 1s. And the configuration of the electrons in the lowest energy situation is the sigma Gerada 1s2 configuration. Again, a configuration is which orbitals electrons are found in. So sigma Gerada 1s2 is the configuration, and associated with this configuration is a single term symbol, and that we call X singlet sigma. So the X here indicates it's the lowest energy term. The singlet is the spin degeneracy, and because the spins are anti-aligned, that's given. This is a singlet. And then the sigma shows that the overall orbital angular momentum about the z-axis of those electrons is 0. It's an overall quantity, so it gets a capital Greek letter sigma. This is the Greek letter indicating that we're talking about molecular orbitals as opposed to atomic orbitals. So that's that for that. Now, if we were to promote one of those electrons and flip the spin so that we had now a spin up electron in that sigma Ungerada 1s, and we left a spin up electron in the sigma Gerada 1s molecular orbitals, then we'd have a configuration that was sigma Gerada 1s1, sigma star Ungerada 1s1. And I always put the ones in there just to be emphatic and explicit about where electrons actually are. So that's a different configuration. But with the spins as drawn, with the spins aligned, there are three ways to have spins, two spins up, right, or two spins aligned. I can have up, up, down, down, and I can have the up and down, but generally in the same direction, so that the z component is 0, but the total spin is 1. So all these have a total spin of 1, and they have a spin degeneracy of 3. So this is the A triplet sigma term symbol here. A being the first excited term symbol. It's a triplet because it's a spin triplet, and then it's a sigma. Now the next thing we can do is erase the green and flip that spin down. So now I have a spin up and a spin down, and if these guys are anti-aligned, it's the same configuration, but with a different overall spin degeneracy, and that's the B singlet sigma. So again, the configuration here is sigma Gerada 1s1, sigma star Ungerada 1s1, and we have an A triplet sigma and a B singlet sigma state out of that configuration. So that then gives us the overall arrangements here. So those spin symmetries matter. Again, the B state is higher in energy than the A state because the singlet spin exchange, having the anti-symmetric exchange symmetry in the spins, requires a symmetrical exchange symmetry in the spatial exchange wave function, and that's the one that has the little cusp and thus has a higher kinetic energy. So the singlet and triplet states, always for the same configuration, you're going to find the singlet higher in energy than the triplet, and there's an example of that. Now the interesting thing here is that so if we go back to our X singlet sigma case where the spins are anti-aligned, or any of these singlet cases, the singlet characteristic of this has to exist from the get-go. I can imagine taking two hydrogen atoms, having them interact with each other, and it's only if the spins of the two electrons are anti-aligned that I am able to form the X singlet sigma bound H2 neutral hydrogen. If the spins are aligned, I'm stuck in a triplet configuration, and I am by definition on the A triplet sigma surface. So even though at large separation there's really no difference between having the spin of one electron aligned or anti-aligned with the spin of the other electron on the other hydrogen, if these are two neutral hydrogen atoms coming to interact with each other, it still matters. And let's look at this in the sense of a different of a geometrical drawing here, where I now have the bond, a nice little Morse function, the bond distance, A and B, energy, and there's my X singlet sigma, my A triplet sigma, and my B singlet sigma um, levels, electronic energy levels here, where the X singlet sigma is the bound interaction of the two electrons, the bonding. We're filling the sigma the sigma Gerada orbital, and with the A triplet sigma and the B singlet sigma, we've filled both the sigma Gerada and the sigma star Ungerada, so we have no bond, and it's a purely repulsive surface. If we think of this starting with two neutral hydrogens far, far away, coming at each other with some amount of kinetic energy, so we've got this red amount of energy, which is usually a very small amount above the 0 point, above the value at infinite separation, because typically the amount of energy associated with things is about kT, which is a couple hundred wave numbers, and remember this well is about 30,000 wave numbers deep, so very, very small amount of energy there. And these hydrogen atoms are coming at each other, and I might imagine that either I'm occupying the singlet, the triplet case, in which case one of my electrons is in this Ungerada sigma star molecular orbital, and the other one is down here in this bonding Gerada sigma Gerada orbital, or both of them are in the bonding sigma Gerada orbital. But at large separation, it doesn't make any difference at all, because the spatial overlap of these atomic orbitals is a major part. It's what's driving the interaction energy, and we'll talk about that more in the next video as well. So when there's no spatial overlap between these orbitals, when the atoms are far, far, far apart, there is no energy difference at all between those two cases. Remember that completely separated double well I assigned on the first, I think it was, exam? There's no difference in the ground state energies of those two wells when they're completely separated from each other. It doesn't matter if the wave function goes up in one well and down in the other well. It doesn't matter if it's up and up or up and down, but it sure does matter once they start to overlap with each other. So as the hydrogens come closer and closer together, you might imagine that they're going to come together and they're going to bop off of this this what we call repulsive wall when the nuclear charges eventually force the issue and repel the system. And actually a really interesting thing about neutral atom collisions is I've got to do something with all that energy. So as the system comes along, it conserves total energy. We move along this red coordinate, and notice that the kinetic energy, which is the difference in the red and the purple, gets really, really big. So the two atoms are moving incredibly rapidly. They've got an enormous amount of kinetic energy just as they're over the equilibrium bond distance. So they'd love to make a bond. They'd love to drop down into that well, but they can't do it. There's no mechanism to get down there into that well. You have to get rid of that energy somehow, and you're going to do that by colliding with stuff. And this whole thing is over in a femtosecond. There really isn't enough time to collide with anything, so they bop off that far wall and come sailing back apart. Now the interesting thing is that actually happens in only 1/4 of the collisions. 3/4 of the collisions, instead of coming way in and hitting that repulsive wall, they move apart at a large interaction distance. About 3/4 of the time the system is in the triplet state, and the two hydrogens coming together will instead of having the kinetic energy rise to an enormous value, it'll get sapped away as that triplet energy rises, and the system will just kind of, it's almost like it's got airbags. And the two hydrogens get nowhere close to each other at all. And you can do these things in what are called cross-molecular beam experiments. And you might imagine there's an enormous difference in the way that these two atoms bounce off of each other, the way they scatter off of each other, depending on whether there was this really strong attractive potential pulling them toward each other and spinning them around and scattering things off at all kinds of different angles, or whether they just kind of airbag off of each other like that A triplet sigma. And indeed, we find that because of the greater spin degeneracy of the triplet sigma case, that 3/4 of the collisions look like the triplet sigma collisions, and only 1/4 of the collisions show the signs of that really, really strong, attractive interaction there on the X singlet sigma surface. So it matters how I prepare these spins at really large internuclear separations to what ultimately comes off from this collision. Now there's a really interesting reverse thought experiment here. What happens if I start the system bound and use something like an infrared laser to drive it up to a highly vibrationally excited state? Remember those Beard-Sponer plots? We work our way up the vibrational ladder and we get up to enough energy we can actually break this thing apart. I never flip a spin. I'm not changing the electrons here. I'm just pumping energy into the system. So I don't change my electronic state. I remain on the X singlet sigma surface, and I just push energy into that bond one way or the other. And you can do this. There are various ways you can do it. And so once I get it up there to the energy where it can dissociate, the system is going to dissociate, and I'm going to drive out apart. And I'm going to drive out apart a system that's on the singlet surface. And now you might imagine that I could make two detectors that were very far apart from each other, meters and meters apart from each other. And I can measure a spin. I can tell if it's up or down. It gives a different magnetic reflection. You can tell right away. That's why we call it the magnetic quantum moment. So we can do a very fast measurement that determines whether the spin of, let's say, A, the nucleus on the left there, is up or down. The incredible thing is, at the instant that I make that measurement, I am 100% certain that a person with an instrument at point B, if I measure spin up, I know with certainty that at point B it was spin down. I know that spin. And this experiment can be done so that at the time of that measurement, over the full time of taking the measurement, it's happened in less time than it would take a photon to get from A to B. In other words, faster than the speed of light. I measure up at nucleus A, and I know I will measure down at nucleus B. I'm going to measure up 50% of the time for A and down 50% of the time for A. I have no idea which one I am going to measure. It's a 50-50 coin flip. But as soon as I measure it, with 100% certainty, I know what the answer is at B. And I know it faster than light could have communicated from A to B. This bothered Einstein terribly. He called it spooky action at a distance, and he actually raised this as a counter-argument to the sort of statistical quantum inference of the probability distribution of finding the answers, the expectation values of the spin measurement, the spin orientation in this case, because he said that's a preposterous thing. You can't find that information out faster than the speed of light, because I'm essentially determining what's being done at measurement location B, and I know the answer faster than any information can have gotten from B to me if I'm over at station A. The experiment's been done, it works. So you really do measure down at B if you measured up at A. The reason why it's not any sort of violation of the relativity is that no information is conveyed. I can't manipulate the answer I find at A, and thus manipulate the answer that's found at B. It's a passive observation. Once I observe up at A, I know they must have found out down at B. But there's nothing I can do about it. It's just knowledge. It isn't information. And that actually matters. It makes a difference. And to everyone's great delight, the theory of relativity nor the theory of quantum mechanics are violated by that finding.